Okay, welcome back guys to this video. We're going to cover question 3 from the IEB physics paper supplementary from 2015. So let's get into this question then. Okay, so essentially the question says that this vehicle is able to accelerate from 0 to 83.3 meters per second in a time of 13.63 seconds. Then there's a nice picture of the car. Then we can get into our first question. Let's start with question 3.1. So we have to convert 83.8 meters per second to kilometers per hour. So how do we do that? We go 83.8 meters per second times 3.6, which is equal to 301.68 kilometers per hour. Okay, if you ever wonder why we multiply by 3.6, this we do through dimensional analysis. So essentially what we start with, let's do a different color, we start with this meters per second, right? And the final answer we want in kilometers per hour. So we want to get rid of this meters and we want a kilometer at the top. So we replace it with a kilometer, which has 1000 meters. And then we want to get rid of the seconds. So we put a seconds up there. And we want an hour at the bottom, and 1 hour has got 60 times 60 seconds. Okay, then we cancel these, so these end up cancelling, so we're only left with kilometers, and we're left with hours at the bottom, and this is equal to 3.6 kilometers per hour. So that's how we get to this 3.6 value, but I think most of us just learn it as a rule, but it's also important to know how we actually get there. But that's the answer to the first question. So moving on to question 3.2. Calculate the distance covered in meters during this period of rapid acceleration. Okay, so this is a simple UVAT. So UVATS. Okay, the initial velocity is 0. The final velocity is 83.3. The acceleration is unknown, the time is 13.63, and the distance is what we're looking for. So what formula can we use? We can use S equals a half U plus VT. So we have a half 0 plus 83.3 times a time of 13.63. And this gives us a distance of 567.69 meters. Which is the answer. Okay, let's go on. So question 3.3.1. Okay, so it says the stopping distance is the sum of the reaction distance and the braking distance. The reaction distance is how far the car travels before the driver reacts and applies brakes. Okay, and then we've got a table of it. Cool stuff. Then it says state the relationship between reaction distance, so between reaction distance and speed. So if we actually just look, we can try and figure out a relationship between the two. Sorry about that. Okay, so if we actually look at the two, we can find a relationship. So as we can see, as the speed increases, our reaction distance actually also increases. So that we can put down immediately. So as speed increases, our reaction distance increases. That is a relationship on its own. But we can actually go a bit further, and we can say that if we look at the speed and the reaction distance, we can see that the speed times 0.7 is actually equal to the reaction distance. Just check that with the first one. So the speed of 10 times 0.7 is equal to 7 meters, and a speed of 40 times 0.7 is equal to 28 meters. So we see that it holds for most of it. So what we can say then is that because we have a constant here, we can say that the reaction distance is actually directly proportional to the speed. It's important that we have the variables in this order. If we had speed at the beginning, this would not be correct. The speed isn't actually proportional to the reaction distance. It's the reaction distance that is proportional to the speed. That's an important distinction that needs to be made. So that's the answer to that question. Okay, moving on to question 3.3.2. Okay, so we've been given an equation v squared equals u squared plus 2as, and we have to determine a mathematical relationship between the braking distance and the initial speed of the car, which brakes uniformly to rest. It's going to be quite important. Use the equation to prove this. Prove that the braking distance is directly proportional to the initial speed squared. So essentially we want a relationship of s versus initial speed, which is u squared. So let's manipulate this formula to get s as the subject of the formula. So we can say that v squared minus u squared equals to as. Solving for s, we can say that s is equal to v squared minus u squared over 2a. But it said that it gets to rest. So we can say that where v equals 0, we have the relationship s equals minus u squared over 2a. And it accelerates uniformly, so we know that a is constant. And 2 is obviously also a constant, so we can actually say that s is equal to, let's group the minus sign with 2a, 1 over minus 2a u squared, and we let that equal to k, so s is equal to k u squared. So we've shown that s is directly proportional to some constant times u squared. And that has been shown. Okay, then it says use the data in the table to prove that these results obey the relationship. So essentially, we had a relationship between speed. So we had a relationship between speed and braking distance. So speed and braking distance. So we need to solve for k. So from our previous question, we can say that s equals k u squared. So s equals k u squared. Okay, so we're looking for k. So k is equal to s over u squared. Now from our table, let's put some points through. So let's have s, u squared, and k. So for the first one, our speed would be 10, u squared would be 7 squared. Okay, sorry, that's not correct. So where's that? But our s would be 7, braking distance is 7, and our u squared would be 10. So we're taking this and we're putting it there because this is distance. So we have 28, 63, 112. We have 20, 30, and 40. If we just look at the first one, s is 7 over 10 squared, which gives us 0.07. If you go through all of these, you actually get 0.07 for all of them. So you can see that it is directly proportional with a constant. So that's essentially what we need to prove. Okay, for the next question, 3.3.4, the stopping distance given in the table are just a general rule. Give one factor other than speed that would affect the reaction distance. Okay, let's think about this. So reaction distance is the time it takes for the person to react. So what kind of things could affect the reaction distance? So some things like visibility. So if it's not very visible, if there's a rain, if there's mist or something like that, he's going to take longer to react. Other things can be, well, the driver may not be in a good mental state, so the mental state of the driver may be an effect. We can think of alcohol consumption. So if the driver is intoxicated, he'll probably or she'll probably take longer. And another thing could be the tiredness of the driver. So the more tired you are, the less likely you'll react well. That's for A, and this is for B. Give one other factor other than speed that would affect the braking distance. So what would affect the braking distance? I would say things like the wear of the tire can have an effect. Another thing could be the road conditions. So if the road is wet, it may take longer, or if the road is tar compared to concrete, there's different factors. And then also the conditions of the brake conditions. If the brakes are worn, then it'll take longer to brake. So these are things that you can consider. Okay, so that question is also now done. Okay, now we've got a nice long question for 6 marks. Let's do it on this side, not this side. Okay, so question 3.4. Okay, so the Bugatti Veyron is known for its ultra-fast deceleration. Okay, so we have a driver essentially, whilst traveling at a speed of 113 meters per second, James sees a fallen tree 600 meters ahead. He takes 0.7 seconds to react before slamming on his brakes and decelerating at 12.1 meters per second squared. By means of suitable calculations, determine whether James hits the tree. Okay, so there's some information given, right? So we know that his initial speed is 113 meters per second. We know that his time for reacting is equal to 0.7 seconds. And then we know that his acceleration is equal to 12,1 meters per second squared. What do we know about acceleration? He's decelerating, so it's going to be a negative. Okay, so let's think about this. For the first 0.7 seconds, he hasn't applied the brakes, so he's just traveling at constant velocity. So we can say that for the first part of his travels, let's just make a nice, not very straight, but we have a tree here, and we have James here. And let's this 1, this is 2. So for his first part of his travels, we know that he's traveling at constant velocity. So we can say that speed equals distance over time. So the if we want to work out the distance, that's equal to speed times time, which is equal to a speed of 113 times a time of 0.7 seconds, which gives us 79.1 meters. So what we can say is to this point, to that point, he's traveled 79.1 meters. And the total distance here is 600 meters. Okay, so for the second part of his travels, he's decelerating. So let's just use some UVATs. So if we have UVATS, his initial velocity is 113, his final velocity is 0, his acceleration is minus 12.1, and time is unknown, and distance is what we're looking for. So what formula can we use? Let's use S equals UT plus a half. Sorry, can't use that one because we don't actually know his time. So let's try a different one. Let's see if we can use V squared equals U squared plus 2AS. Okay, solving for S, we have S equals V squared minus U squared over 2A. So V is 0 squared minus 113 squared over 2 times minus 12.1, which gives us a distance of 527.64 meters. Okay, so his distance here, just this distance, is 527.6 meters. So now let's work out his total distance. So S total is equal to S1 plus S2. So let's give these subscripts S1, S2, which gives us 79.1 plus 527.6 0.64, which gives us a total distance of 606.74 meters. Okay, so what does this tell us? This tells us that in his last section, he actually goes past the tree, because the tree only makes it to 600 meters, and he needs an extra 6.74 meters. So what we can say is that, therefore, James will hit the tree. And this would be our final answer. Okay, and that's that. So in the next video, we'll go through the next question. Thanks for watching, guys.